All right, this is exam 1 for spring 24. First, the free response. I want you to sketch the E field vectors, the electric field vectors at point A, and then show any angles. So remember, for the electric field, we're imagining that there is a positive charge right here. And I asked myself, what is the direction of the force that's felt on that positive charge? Due to this minus 50 nanocoulomb charge, that force, or excuse me, that force would be in that direction. So that is also the electric field. I'll call that E1. And then due to this positive charge, that force would be repulsive, and so the electric field is likewise in that direction. So I'll call that E2. Now I also want to calculate any angles. That would be this angle right here. Recognize that that is a triangle, is a 3, 4, 5 triangle, and I want to know what this angle is. So I do the inverse tan of opposite over adjacent, or 4 over 3, and that's going to be 53 degrees. So that angle is 53 degrees. So effectively just drawn, a free body diagram. Let's just sketch there's our y-axis, there's our x-axis. So those are my two force vectors on that free body diagram. Now I want to show you work for calculating the x and y components. So this was part A right here. For part B, first you want to find what are the magnitudes of E1 and E2. E1 is going to be kq over r squared. It's going to be 9 times 10 to the ninth times q, which is going to be 50 times 10 to the minus 9, divided by that distance. It's a 3, 4, 5 triangle, so that's 5 squared. I can get some cancellations here. That's 25 divides into 50 twice, so that gives me 18 um, newtons per coulomb, or volts per meter, either would be correct. And then for E2 is very similar. Q is 32 times 10 to the minus 9, divided by the distance, which is 4 meters. That's this distance, which is 4 meters, squared. Those cancel. That 16 goes into 32 twice, and I also get same answer, 18 newtons per coulomb. So this is 18. This is also 18 newtons per coulomb. Now I want to find the x and y components. So look, I'm just going to redraw my coordinates right here, and we will now write in our x and y coordinates. So e2y is equal to 18. It's actually negative 18 because it's in the negative y direction. E1x is going to be 18 times cosine of 53. Let's see, 18 cosine of 53, that's 10.8. Let's see, I guess I should just be keeping 2 sig figs. I'm gonna keep 3 until the end, but if you kept 2, that's fine. And then this is the y component. E1y is going to be 18 sine of 53, and that's going to be 14.4 newtons per coulomb. All right, so those are, no, not quite done. So I need to know the x and y components of the next vector. I'm not sure if this is part B or C, it doesn't really matter, but the next step is to figure out what is the x component and the y component of the resultant vector. And the y component is going to be 14.4 minus 18, and the x component is going to be negative 10.8. So this is what? Negative 3.6. So if I redraw that again, pictures are always your friend, y'all. Draw lots of pictures. Then I get my x component is in this direction at 3.6. My y component is in this direction at 10.8. So those are the x and y components. Now, I guess that would be part C. Part B, rather. This is the answer for part B. Now for part C and D, we'll do those sort of together because I want to find the magnitude and direction of the electric field at point A. Well, that's going to be what is the length of this vector, and then what is this angle? I'll call this theta, but then I also want to know what is this angle because I want to know what counterclockwise from the positive x-axis. So to find that, I say that the electric field is the square root of 3.6 squared plus 10.8 squared. And I find that that's equal to 11.4 newtons per coulomb. And then that's the magnitude of the electric field. And then the angle theta is the inverse tan of 10.8 over 3.6, which would be 72 degrees or 71.6 degrees. Sorry, I'm being a little shoddy with my um, sig figs. That's below the negative x-axis, and then I really wanted it measured counterclockwise from this axis, so I'm going to add 180 and 72, so that angle is actually, I'm going to call it phi, is 180 plus 72, which is 252 degrees from the plus x-axis. So that is the magnitude. I would take 11. This is the direction. I would take 250 for that. So the final part of this question for part E is to find the potential. And remember, to find the potential, I find the potential due to this charge and to that charge. So that's going to be 9 times 10 to the ninth times 50. I think that was a negative charge actually. Negative 50 times 10 to the minus 9 divided by the distance to that 50 nanocoulomb charge, which is 5 meters. It's kq over r, so this is my total potential, plus 9 times 10 to the ninth times, what was it, 32 times 10 to the minus 9, divided by the distance, which is 4 meters. So let's see, that cancels 10, cancels, so it gives me negative 90 plus, what's 9 times 8, 72, is negative 18 volts. So that's the right answer, negative 18. All right, let's catch 5 to 6. Oop, 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 oop. 5 to 6 electric field lines. I start at the positive and go to the negative. I'm going to draw a couple more. But recognize that the 2Q charge is twice as big as the 1Q charge, so it should have twice as many electric fields. So it's going to look sort of something like this, with those arrows going in. I'll draw it since how many I asked for? 5 to 6. We'll just stop there. And then you could have drawn another one, that's fine. Draw the electric potential line, like green. So the equipotential line, as you go around, at each point, it should be perpendicular, like that. So here, for example, it's going to flatten out a little bit. It's going to curve over here, but not as much as it did around the minus 2q. So it's going to sort of look like that. Almost flat there. I'm going to ask for 4 to 5. Yeah, that'd be okay. You could do some on the left or right of those, but that's fine. All right. So proton moves from point A to point B, as in this figure. Moved a distance of 0.01 meters. Electric field is reading as constant. What is the speed of the proton? So I know that the change in potential, or excuse me, that my change in potential is equal to delta PE divided by Q. That's just sort of a big idea of what is potential. That is energy over charge. And so my change in potential energy is going to be equal to Q times delta V. And that's also going to be the negative of my change in kinetic energy, but that doesn't really matter that much here because I'm dealing with scalar quantities. So I'm just going to drop the negative altogether and just say that the change in kinetic energy is equal to Q delta V. That is 1/2 mv squared, that's the speed now, is equal to Q delta V. I can put in some numbers here. So 1/2 of the mass for a proton, that's 1.67 times 10 to the minus 27 kilograms. That's on your equation sheet. It times V squared is equal to 1.6 times 10 to the minus 19. That's fundamental unit of charge, times delta V. Delta V, I'm going from 5 to negative 5. So I have a delta V of negative 10 volts. But again, because I did this switcheroo with a sign right here, because my change in kinetic energy is the negative of my change in potential energy. But it turns out that the signs don't really matter. So I'm just going to drop that negative, that my magnitude in the change in potential is equal to 10 volts. And then if I solve that for V, when I solve that for V, I get that V is get that V is 44,000 meters per second. All right. Then I want to know what is the electric field in this area. Well, the potential and the electric field are related in this way. This is a relationship we saw early on. In fact, if you remember that we said that E was equal to V over delta X, that's where we get those other units, volts per meter, for the electric field as opposed to newtons per coulomb, the relationship between V and our displacement. So if I want to know the electric field, I say that the electric field is V over delta X or delta V over delta X. I'm just looking for the magnitude of it. And so that's going to be, I don't need to worry about the signs, 10 volts over zero point zero 0.01 meters. And that gives me an electric field of 1,000 newtons per coulomb. And I already know the direction is going to be to the right there. Let's look at multiple choice. Two charges experience force, 12 newtons. So I'm going to write down my equation first. If I have one of the charges and move the charges to half their original sum, having the distance and having one of the charges. So in the end, I get 1/2 divided by 1/4, which is 4 divided by 2, which is 2. So I'm getting something that's twice the force, so it's going to be E. Which vector best represents the force vector? Well, both of these charges are the same distance and they have the same magnitude. So both will exert the same force on the plus 2q. So I can draw a force here on the 2q and a force here on the 2q. Both of those are same magnitude. So the answer is going to be the one that lies in between those two. What is the magnitude and direction of the force on the 3 times 10 minus 5 coulombs charge? So I just want to know the net force. Let's just draw the forces here. F1 is down, F3 is also down, so I need to calculate what those two are. F is going to be equal to KQQ over R squared. Notice though, I'm going to make this a little simpler, that I made these 10 to the minus 5, 10 to the minus 4, that's 10 to the minus 9, so it cancels out with my 10 to the ninth and the K. So just let me show you what I mean by that. So I'm going to write this a little bit differently. 9 times 3 times 4. Oh, I'm sorry, not 4. I was doing the next one. 9 times 3 times 3. I just canceled these out with the 10 to the ninth and the coulombs constant. Divided by the distance, which is 3 meters squared. So that cancels with that and gives me 9 newtons. Yeah, let me just make sure that's clear. So the way I did that math, I said 9 times 10 to the ninth, 3 times 10 to the minus 5, 3 times 10 to the minus 4 divided by 3 squared. And then these canceled with that. And then this canceled with both of those and left me with 9. I just do that to make the math a little easier. And then also F3, the force due to particle 3, is going to be 9, 4, 3 divided by 6 squared. That's 36. That's also 36, so it leaves me with 3. So I get 9 plus 3, but they're both in the negative direction, so it's going to be 12 newtons downward. If you're not clear on what happened here, it's similar to what happened here, so just write it out longhand with all the scientific notation. What is the direction of the force acting on Q2? Well, that force is acting up and in this direction. Let's figure out what this angle is. So it's 53 degrees above the negative x-axis. Yep, that's the right answer, C. Where is the electric field equal to 0? Okay, well, we just sort of have to draw it. Here, the electric field is in that direction, and it's in that direction, not there. Here, in that direction, that can't go to 0. Likewise, D can't go to the 0. C, oh, I should do B. I have sort of that direction and that direction. Now, let's look at C. So I have the electric field due to minus Q is in that direction. The electric field due to 4Q, which is twice as far away, and remember electric field is KQ over R squared, so I have 4 times the charge, but it's twice as far away, so that gives me the same electric field. These are equal and opposite, so it is that answer. It's really the only possible answer. All the others have vectors that are not even along the same line, so C is the only possible answer since there isn't a none of these. What is the sign and magnitude of Q3? I'm told that Q1 is 12, and I know that that's positive, and Q3 must be negative, so I can, oh, not that one. I can get rid of some of these. I can get rid of the positive ones, and then notice I have 1, 2, 3, 4, 5, 6 lines. So I like to think of it as like 2 coulombs per line. And then I only have one line here, so that means it must be negative 2 coulombs. Because my charges have to have a 6-to-1 ratio because I have 6 lines coming out of Q1 and 1 line going into Q3. By the way, this Q2 would be negative 4 coulombs, if you're curious about that. 2-point charges each have a value of 30 millicoulombs and are separated by a distance. So I have a charge here and a charge here. I want to know what is the electric field, but each of these are 30 millicoulombs. That means that the electric fields are equal but opposite, so the answer is B. If this particle experiences a force due to the electric field moves to the left, what is the charge of the particle? Well, if this was a positive particle, it would move in that direction. If it's a negative particle, it would move in that direction, so that's the right answer. See a certain distance. So anytime you see these, write the equation. Then ask yourself what's changing. The charge is doubling. And your distance from the charge is also doubling. So I get a 2 in the numerator and a 4 in the denominator. So it's D. That is yes, no. That would be 0, the charge of a neutral atom. Yes, and obviously no. So 1 and 3. No, that would be charging by conduction. No, that would be electrons. Just in general, difficult to make protons move around. Yes, that's why they're conduction electrons, because they can move around. And a conductor has more electrons than no. So uh, not unless it's been charged, but no reason to think that that's the case. So let's see. 3. A is the right answer. This figure shows how particles A and B respond to one another, and separately how A and C respond to one another. So which of these statements is true? All right, so first of all, I know that A and C are opposite. That's not correct because they have to be like charges for that to happen. And A and B have to be opposite charges for this to happen. So what B and C, are they opposite or like charges? So I always like just imagine, what if this one's positive? If that one's positive, that means that one has to be negative. And if that one's positive, that means this one has to also be positive. Or you could have chosen the opposite of A being negative and you would get the same answer. But that tells you that B and C are opposite charges. See, because it's negative here and positive here, so they're opposite. Right here, you're just calculating the capacitance. Simple. Just write out the equation. Make sure we know what all those values are. 1.2 epsilon naught is on the equation sheet. A is 0.3, and then the distance is 3 times 10 to the minus 6. Being careful with your order of operations on your calculator, or of course using that EE button, that exponential button that allows you to do scientific notation more easily. And so for that one, we get that it's equal to 1.1 times 10 to the minus 6, or 1.1 microfarads. So here, remember, Q is equal to C times V. That's how we define the capacitance, or one of the ways we define the capacitance, and calculate the amount of charge on it. The one with the most charge is the one, if they're identical, the one with the bigger voltage. So A is the right answer. I think we had that question on a concept test. What's the purpose of a dielectric? Yes, keep two plates from touching. So remember, we have a capacitor. The dielectric goes between them to increase the capacitance of a capacitor. Yes, that's true. C is equal to kappa C naught. So if without the dielectric at C naught, you just multiply it times that dielectric constant. To increase the voltage on a capacitor, that might be the case, but not necessarily. And to produce a current, there is never a current in a capacitor. If a capacitor has a current, it means that the capacitor is no longer functioning, that there's never a transfer of charge from one plate to the other. The potential at point A to be 0, what must Q2 be? Okay, so first we want to calculate what are the potential due to these two charges, and then the potential due to Q2 has to be equal to that, but opposite, but negative. So I'm just going to do V1 is 9 times 10 to the ninth, 25 times 10 to the minus 9. And remember, I'm keeping my negative there, divided by this distance, which is 5 meters by 5. That cancels. 5. That gives me negative, what's 9 times 5? 45. So that's V1. V3, 24 times 10 to the minus 9, divided by 4. That's 54. And that is positive. So I get V1 plus V3 gives me 9 volts. That means that V2 must be negative 9 volts. So I'd say negative 9 equals Q2, or 9, shoot, sorry, 9 times 10 to the ninth, Q, divided by the distance, which is 3. So assuming this is nanocoulombs, that'll go away. That becomes 3. 9 divided by 3 is 3, but it's negative 3. So yeah, negative 3 nanocoulombs. This works out to be Q is equal to 3 times 10 to the minus 9, uh, negative 3 times 10 to the minus 9. These three charges are all equidistant from one another. So distances are the same. What describes the potential energy? Is it positive or negative or zero energy? So each configuration of charges, these two, and these two, they all have some potential energy. And that potential energy is given by K, Q, Q over R. K and R are going to be the same for all these. So I'm just going to take the product of Q, and that'll give us an understanding of the relative sizes of the energy. So for example, these two have 16. I guess you could say joules. It's not really joules because we haven't included the K and the R, but it's a measure of the energy. These have negative 8 and these have negative 2. So that's 16 minus 10, or 6 is the energy, positive potential energy. So A is the right answer. Consider you place an electron at point B. So have an electron right there. What direction will it, what will it do? So remember our mountain. Remember our mountain that if we have positive charges, they roll downhill, but negative charges will roll uphill. That is from low potential to high potential. So this is going to, at point B, is going to move up. So it's going to move towards C. So that answer is B for 18. How much energy does it gain? So remember, V is equal to delta PE over Q, or rather delta V is delta PE over Q. So our change in potential energy is going to be Q times delta V, which is going to be 3 coulombs. And then let's figure out what our change in potential is. It's starting at C and it goes to A. So it goes from here all the way over to here. So from 30 to negative 30, or 60 volts, a total of 60 volts. So that's 180 joules. C. And then what point is a potential equal to 0? Well, like for example, right here, um, the distance to these two is equal, so they cancel out, but the distance to these two is not equal, so they do not cancel out. So it's not D, but the answer is right here. Notice these distances are the same, these distances are the same, so those potentials, they all cancel out, and then likewise those are the same. So B is the right answer.